In the next couple videos, we're going to be working through different hypothesis tests by practicing the steps for hypothesis testing. The steps for hypothesis testing are to state the null and alternative hypothesis, specify an acceptable risk of rejecting the null hypothesis when it's true. So what is our alpha? How confident do we need to be? Then we're going to select the test statistic, state the assumptions of the test statistic, formulate a decision rule, draw a graph, and then obtain a random sample of size n from the population, compute the test statistic, and make a decision about the null hypothesis and alternative hypothesis. So we're going to go through over the next couple of videos a number of different hypothesis tests, and then later we will have videos where you can do lots more hypothesis tests. We won't go through all of the steps. We'll just show you how to do the test as we get into more Python coding. But right now, let's look at some one sample tests. We have the Z test, the T test, and a proportions test, and then we'll get into some two sample tests. So let's start with the Z test or one sample Z test, depending on if you're Canadian or American. All right, so when we are doing a one sample Z test, what we are doing is trying to make a statement about the population mean, mu. Now your one sample Z test can be two-sided, which means your null hypothesis can be that mu equals a certain number, or it can be a one-sided test, in which case your null hypothesis will be that mu is greater than or equal to a number, or mu is less than or equal to a number. Remember that your null and alternative hypothesis must be mutually exclusive and collectively exhaustive. So what we need is to cover whatever's not in the null is in the alternative. The alternative is the one that the researcher really cares about. The null hypothesis always includes the equality. So if you think that the average is less than 15, your alternative hypothesis will be mu is less than 15, and your null hypothesis is that mu is greater than or equal to 15. If we are doing a one sample Z test, our test statistic is this z-score that we've seen before, which is x bar, the sample mean, minus what we think that mu is, divided by sigma, divided by the square root of n. And we're using a z-score if we know the standard deviation of the population. So our assumptions here are random sampling, normality, so we have a normal distribution for the underlying population, or a large enough sample size that we can use the central limit theorem, which says the sampling distribution is going to be normal. And the key here with the Z test is the variance or standard deviation of the population is known. In previous videos, we talked about confidence intervals. And so if you are doing a null hypothesis that is equals and an alternative hypothesis that is not equals, then you could find a two-sided confidence interval to go with that hypothesis test. If we are doing a one-tailed test, then we're simply just focusing on one side of that confidence interval, essentially. So if your alternative hypothesis is that mu is greater than 15, then we would look at a confidence interval that was also one-sided, where we have mu here being greater than, and then we calculate that part of the confidence interval. If the alternative is mu is less than a number, like less than 15, then your confidence interval is also going to be one-sided here, where we have mu is less than, and then you calculate that upper bound to that confidence interval. All right, so let's go through an example. So the Minnesota Multiphasic Personality Inventory Test measures the level of psychopathic deviance, a measure of antisocial tendencies. The test was given to a random sample of 30 men classified as habitual criminals. The researchers wanted to know if habitual criminals have greater antisocial tendencies than non-criminals. The population of non-criminals is known to be normally distributed with mean and standard deviation, mean of 50, standard deviation of 10. So we know information about the population. We know the standard deviation of the population, and we know the population is normally distributed, which allows us to use a z-score. And we are looking at the average for the population. So we have a hypothesis test about mu, and so we're doing a one sample Z test. All right, so let's take this one step at a time. Our first step is going to be to state our null and alternative hypothesis. Remember, the alternative hypothesis is what we care about, and the researchers want to know if habitual criminals have greater antisocial tendencies. So we think that mu is greater than, and here we have the mean for the non-criminals is 50. So we think that the average score is more than 50 for criminals, which means the null hypothesis is less than or equal to 50. The next thing we want to state is the level of significance, the type 1 error. How much error are we willing to allow? And recall that when we talk about type 1 error, we are talking about rejecting the null hypothesis when it is true. Okay? And we talked in our previous video about alpha versus beta. So alpha is rejecting the null hypothesis when it is true. So we're saying that they're, in this case, we would be rejecting this hypothesis that they are the same as the non-criminals, that their scores are equal to 50, rejecting that and saying, no, their scores are higher when in fact they're not. That's alpha. Whereas beta is where we are the opposite here. So instead of rejecting the null hypothesis when it's true, we are not rejecting the null hypothesis. So we're saying there's no difference. And when in fact, no difference when in fact there is a difference. So that is the type 2 error. So you sacrifice one error for another. So right now, alpha, let's pick an alpha here of 0.05. That's going to relate to a 95% confidence interval we talked about previously. Okay. All right. So step 1 was to state the null and alternative hypothesis. The second one was to specify an acceptable risk. Step 3 is to select the test statistic. And so here the test statistic is a one sample z-score, z-test. Okay. And we can just write out here that we're doing a one sample z-test. Then we have our assumptions that go with this test. It is random sampling, so we have a representative sample from that population. We have underlying normality or a large sample. Here we know the population is normal, and the standard deviation of the population is known. So we would write out these assumptions here to go with our test. Because if these assumptions are violated, then any statements we make about the population won't be true, and it kind of covers ourselves if any of the assumptions really aren't true, and then our projections are false. Okay, so we did state the null, specify the risk, select the test statistic, state the assumptions. The next is going to be to formulate the decision rule. So what we have here is a one-tailed test. So essentially, if we have this here, then what we're going to do is we're going to find our critical value z, based on alpha. Okay. And it is a one-tailed test where we are looking at greater than. This z alpha will give us that this area here is 0.05. Okay. We are then going to use our formula z equals x bar minus mu sigma over the square root of n to find our test statistic. If our test statistic is bigger than our critical value, we will then reject the null hypothesis and conclude that the average is more than 50. If our test statistic is less than our critical value, then we will not reject the null hypothesis. It is possible that the criminal and non-criminal scores are the same, or the criminal scores are lower. It's also possible we're not detecting the difference because the test we use isn't strong enough, the sample size isn't big enough, or other reasons that we're not detecting the difference that we expect to see. Now, alternatively, instead of comparing your critical value, so actually I'm just going to write this here just so we're clear on what we're doing. Okay, so we are going to reject H naught if our test statistic is greater than the critical value. And then we will conclude that the average is greater than 50. Alternatively, we can reject the null hypothesis if our alpha of 0.05 here is, let's just get used to writing it the other way here. If our p-value is less than alpha. So this area here under the curve is 0.05. We find the new test statistic. We can find the probability of everything to the right. That'll give us the p-value. If the p-value is less than alpha, we reject the null hypothesis and we will conclude that the average is greater than 50. So now we need to run our test. All right, let's start with doing this in Excel. To do this in Excel, we're going to need our critical value. And we're going to need our test statistic. Okay. So our critical value is what we looking up on the normal distribution table, and we can have it tell us that number. So we go normal distribution. And we actually want the normal distribution from the standard normal table, okay? And that standard normal table, right, is where the center is 0 and we're looking at standard deviations. So we want to know the critical value, and we want to know the critical value. We're looking up the z as opposed to looking up the probability. So what we want is not this formula here, but we want the inverse. We want normal S inverse, because that allows us to then, normal S inverse allows us to type in a probability. Now you're typing in the probability of everything to the left. We have a one-tailed test here. Everything to the left is going to be 0.95. Okay, so we talked about before that when we have a 95% confidence interval, the Z we used was 1.96. Now, that was when there was 95% in the center. We want it 95% just on one side. So what we should get is a number that is lower than that, because we're including that tail that wasn't included when we were doing that center the center 95%. So here we're just doing left 95%. So we want to compare our critical value to our test statistic. To find our test statistic, we are going to need to do this calculation here, x bar minus mu divided by sigma over the square root of n. So let's go back to our data, and we're going to need x bar. Well, x bar is just the average of our data, so equals average. Okay. Now, to find our test statistic, we are going to take our x bar minus mu divided by sigma over the square root of n. So the easiest way to do this is in chunks, so equals the square root. Now, we need to know how many different data points we have here, which we can see from participant numbers. We want the square root of 30. That gives us the square root of n. So then we are going to do sigma divided by the square root of n, and sigma is the population. The population standard deviation is 10. 10 divided by the square root of n. Okay. That gives us the bottom part of the formula. The top part of the formula is going to be we're going to take our mean of 55.16, subtract what we are saying we think the population mean is of 50. So then our test statistic is x bar minus mu, which is this number here, divided by our sigma over the square root of n, which gives us this number here. So what we get is a test statistic that is much bigger than our critical value. So our test statistic here, this is a 1.6. 0.64. And the number we are getting in our calculation is actually 2.83, so that's way out here. So what conclusion do we draw? Well, we reject the null hypothesis if the test statistic is greater than the critical value. Our test statistic 2.83 is greater than our critical value 1.64, so we are going to reject the null hypothesis and conclude that the average score is higher for criminals, higher than 50. Okay, so we go with the alternative hypothesis. The average is greater than 50.